All right, welcome to chapter 8. This chapter is on parameter estimates and hypothesis testing. So we have officially moved into inferential stats, and we are going to be learning our first statistical analysis today, called the one sample t-test. So we're going to be taking the numbers that we would get from a sample and comparing it to the population, so to the normal curve. And when we do that, it requires us to make some estimates about the parameters that we would get if we measured a population. Now, of course, that's theoretical because we can never measure an entire population, as you know. But we can estimate the parameters. And so we're going to be learning about some parameter estimates today, as well as doing our first statistical test, the one sample t, for hypothesis testing. So let's dive in. Exciting day. Okay, so the first parameter estimate that we're going to talk about, again, it's an estimate because we can never measure an entire population. But the first parameter estimate that we're going to talk about is the population standard deviation. So the standard deviation and the mean of a population, of course, is an estimate because we don't have all the scores in a population. This is why this kind of branch of statistics or category of statistics is called inferential statistics, because we are estimating. We're taking what we know from a sample and we are inferring that those results would also be found in a population. And so that's where we get the term inferential. So if we want to estimate the standard deviation of the population, and you'll notice there's that Greek symbol there, the sigma symbol. So that's just letting us know that it isn't just a standard deviation of a sample, because if it was, it would just say SD. But this is the standard deviation of the population, and I know that because it's a Greek symbol, and Greek symbols represent population parameters, or the numbers that we would get if we could measure a population, or they can also be called parameter estimates. Okay, so when we're estimating the population standard deviation, represented there by sigma, the sample standard deviation tends to underestimate the population standard deviation. In other words, we would expect in most cases, if we have a normal distribution, that the population standard deviation would be larger than the sample standard deviation because you have more people in a population, so you would expect there to be more variability, right? And so we would expect the population standard deviation to be a larger number than the sample standard deviation. So that's why we're saying the sample standard deviation tends to underestimate the population standard deviation. And so this is due to sampling error, which, as you remember from the previous chapter, is not an error. We expect the sampling statistics to be different than the population parameters, because it would be just like a little too weird and coincidental if the standard deviations were exactly the same and the means are exactly the same, like we talked about in the last chapter. So since the sample standard deviation underestimates the population standard deviation, it is called a biased estimator. And so to correct for this biased estimator, we just subtract 1 from n, and you'll see that in the majority of the formulas going forward. And so it's, again, just to correct for the idea that there's going to be less variability in the sample than the population just because we have less people. So that's what that means when you see it in the formulas. And here are the formulas. So there you see the n minus 1, and that is to correct for that biased estimator between the sample standard deviation and the population standard deviation. But like we talked about before, we cannot sit down with all 6,000 students at Omega College and ask them, to take an IQ test and collect that data right there on the spot. It's just not practical. For all the reasons that we've discussed. People got to go to work, people are sick, people are out of the country. So because we can't just sit down with all 6,000 people in a population at once, we need to do sampling. And so with sampling, like we talked about in the last slide, we're going to take all 6,000, or I'm sorry, the last chapter, we're going to take all 6,000 of those Omega College students, put them in a fishbowl, and we're going to start pulling 30 names out at a time in sampling groups of 30 people at a time. And then the means that we collect from those samples are going to comprise our distribution. And so we're going to see those means on the x-axis when we're making our histograms and stuff for the sampling distribution. So we make this sampling distribution again because we can't sit down with all 6,000 students of Omega College at once. So we compromise and we go, all right, we'll just take 30 at a time. So if you have the means from the first group of 30 students that you pulled their names out of the fishbowl and you gave them the IQ test, you have their mean for that IQ test. Then you have the next group of 30 people and the mean for their IQ test. And the next group of 30 people and the mean for their IQ test, and so on and so forth. And so you have all of these means. If you wanted to, you could calculate the standard deviation of all those means. In other words, the standard deviation of the sampling distribution of means. And so that symbol that you see on the slide there, it's the sigma and then the subscript capital M. That's the symbol for the standard deviation of an entire distribution of means. However, it's really unlikely that we're going to be able to get an entire distribution of means from a population and it include everyone in that population. So we normally then have to estimate the standard deviation of those distribution of means from a single sample. And when we do this, it's called the estimated standard error of the means, and it's symbolized as SE and then a subscript capital M. And so the formula that we're going to use for the standard error of the mean is the highlighted one on top if you are given the standard deviation in your data set or in the word problem on your quizzes or homeworks. So if you're given the research hypothesis and then the standard deviation, then you would just go ahead and use the formula that's highlighted in this like minty green color. If you, which is the top one, and then the bottom one here that says simplest raw score formula, this is the one you use if you are not given the standard deviation in your word problem. So if you're just given raw scores, you're going to use this formula on the bottom, which if you look at it closely, it just includes the standard deviation calculation that we've been doing, and then that is divided by the correction for the biased estimator caused by sampling error. So you're just going to make sure that you use the right formula depending on what information is given to you in the word problems on your quizzes and homeworks. And then if you look in this little starburst over here on the right side of the screen, it says that a standard error of the mean can't be negative in the same way that a standard deviation can't be negative. So the standard deviation is telling us the variability of a sample, and as we know, things either vary or they don't. You can't have less than 0 variability. And the standard error of the mean is estimating the standard deviation of a sampling distribution of means, or the population, right? And so the standard error of the mean can't be a negative number either, because it's a measure of variance of the population means, or the estimated population means. And so things either vary or they don't. You can't have less than 0 variance. So if you get a negative number when you're calculating the standard error of the mean, it just means that you missed a step, probably forgot to square something or take the square root of something. So just double check your work if you get a negative, because there's not a lot of opportunities in stats to check your work and know if you're right or wrong as you go along. So I always like to point them out when they pop up, and this is one. So no negative standard error of the means. All right, so go ahead and grab your standard error of the mean worksheet off of Canvas, and then we will do the tutorial together right now. Okay, welcome to the standard error of the mean worksheet. So for problem number 1, we're going to find the standard error of the mean. In other words, the estimated standard deviation of the entire distribution of sample means for the following data. So these numbers here represent 15 students' attention span in minutes. So student A could pay attention for 10.9 minutes, student B could pay attention for 10.1 minutes, so on and so forth. And we are going to calculate the standard error of the mean for this, and we're going to use this formula here to do it. And so what we're going to need to do first is identify which of these puzzle pieces we already have. So I have N already given in the data, in the research design here. So 15 is N, 15 students, so 15 is N. Another calculation that we'll need is the mean, so that we can square it and add it to this formula. So for the mean calculation, we're just going to add up all of these raw scores. And so if I add up all these raw scores, I'm going to get 152.90. And then to calculate the mean, I'm going to divide by 15, which is the n. And that is going to, let me label this n. And that is going to give me a mean value of 152.9 divided by 15 is 10.19. Okay, so I'm going to put this value here in the mean, 10.19. And the next step is to square all of my raw scores and then add them together. So if I were to go through each of these, 10.9 squared is 118.81. 10.1 squared is 102.01. 9.2 squared is 84.64. 13.6 squared is 184.96. 9.9 squared is 98.01. 9.7 squared is 94.09. 13.8 squared is 190.44. 13 squared is 169. 5 squared is 25. 6.6 squared is 43.56. 8.6 squared is 73.96. 14 squared is 196. 8.5 squared is 72.25. And 9.9 squared is 98.01. And last but not least, 10.1 squared is 102.01. Okay, so then I would need to add up all of these values. So I'm going to do that here, and symbolized by sigma x squared. And so when I add up all those values, I'm going to get 1,652.75. Oh, I should just put it on this line here. 1,652.75. Okay, so I'm going to refer back to my formula. It says I need sigma x squared. I have that. It says I need n. I have that. And it says I need a mean. So I have that. So I'm all ready to plug in my puzzle pieces into this formula, calculate through, and find that standard error of the mean. So I'm going to begin by drawing my square root symbol. And standard of the mean equals. So for this numerator of my numerator, it's my sigma x squared value, so 1,652.75. And that is going to be divided by n of 15. And we're going to subtract the mean squared from that. So the mean is 10.19 squared. And we're going to divide all of this by our correction for the biased estimator, n minus 1. Okay, so let me plug in the n of 15. All right, okay, so now we can start calculating through. So if I do the division on the numerator here, I'm going to get 110.18. Oh, I better stop and put in my square root symbol. It often gets lost along the way if I don't put it in first. Okay, so minus my mean squared. My mean squared is going to be 103.84. And then that's going to be divided by 15 minus 1, which is 14. And then when I do that subtraction on the numerator, I'm going to get 6.34. And then just carry down my denominator. And when I do the division there, I get 0.45. And when I take the square root of 0.45, I get my standard error of the mean of 0.67. So I'm going to put 0.67 up here. And now I know that the standard error of the mean for these 15 students' attention span is 0.67. So in words that you can understand, what does this number tell us? And so I'm going to give us a little template that we can work with here. If we needed to describe standard error of the mean in the future, you could just use this template and plug in the correct variables and values. So what I would write for this is in a population of students, the estimated average attention span is 10.19, because we're just going to use the sample mean to estimate the population mean here. It's called a point estimate when we do that. Best way to estimate the population mean is the sample mean. So now that I have that, it's 10.19 minutes to be specific. Okay, and when students vary from this mean, it is by 0.67 seconds on average. Okay, so in order to turn this into a template, you just have to know that you would need to describe your population here. So this is a changeable word. You could always describe it as in a population of, and then describe the population. In this case, it's students, so I underlined it. The estimated average, and then this is where you're going to describe the variable and its value. And then when students, again, this is the population, so this word is interchangeable with whatever is being described in the research problem there. So when students vary from this mean, it is by, and then again, you would put the variable and its value. So that is a template for what a standard error of the mean tells us. All right, so that is the standard error of the mean. And now we are going to talk about how we can estimate the population mean. So the way we estimated the population standard deviation was with the standard error of the mean. And now we're going to talk about how we can estimate the mean of the population. And estimating the standard deviation only has one method, but estimating the population mean has two methods. And so this is the next parameter estimate we're going to discuss. So when we're estimating the population mean, we have these two options. The first one is called the point estimate, and the point estimate is so easy that it stumps most people. So pay special attention to this because you're going to be asked questions about the point estimate on your homework, and it's going to be the easiest thing you learned today, and so the most likely thing to forget. So it's going to be on your homework and your quizzes. So make sure you know point estimate. So the point estimate is the sample mean, that's it, and it is the most precise estimate of the population mean. So if you want to know what the population mean is, your best bet is just to look at the sample mean. We would expect that the sample mean is going to be pretty close to the population mean. So it's going to be the best estimate, and that is what we like to use to estimate that mu. You see the mu symbol there, which just, again, stands for population mean. So all you need to do if you're looking at a word problem and it asks you to estimate the population mean is just calculate the sample mean. Or if it's given, just write it down as your answer, which feels weird. So that's why a lot of people get it wrong. But just the sample mean is the best estimate of the population mean. The second option for estimating the population mean is called confidence intervals. And with confidence intervals, a range of values is estimated within which it is assumed that the population mean, or mu, is contained. So the goal is to bracket the population mean within a specific bracket of high and low sample means. In other words, coming up here, I'm going to give you a formula and we'll do a worksheet tutorial on confidence intervals. But that formula is going to have you calculate two numbers, a higher number, which is going to represent the upper limit of your bracket or range. And then it's also going to have you calculate a lower number, which is going to represent the lower limit of your range or your bracket. So the confidence interval formula is going to render you two numbers, and what you're saying when you do that calculation is that you're estimating the population mean to be somewhere between these two numbers that you've just calculated. And there's two types of confidence intervals. There's the 95% confidence interval. So there's a specific formula for a 95% confidence interval. You do it, you get your two numbers, and then you say that you're 95% sure that the population mean falls between those two numbers. Your other option is a 99% confidence interval, which is where you do the formula for the 99% confidence interval. You get two numbers, and then you say you're 99% sure that the population mean falls between these two numbers. So the interesting thing about the 95 and the 99 percent confidence intervals is that you would assume that the 99% confidence interval is like the better one to report. If you were to ask me, like, hey, you're a statistician and I want to have a we could just use the example on the slide. You want to have a 4th of July picnic next year, and you want me to predict for you what the temperature will be next year at 4th of July. And so if you said that to me, I could say to you, well, yeah, I could predict what the weather will be next 4th of July for you. Do you want that to be with 99% confidence, or do you want me to predict that for you with 95% confidence? And you would think that the answer would be 99% confident, like I want you to be more sure of what you're telling me the temp is going to be. But the thing about the 99% confidence interval is that it comes with a catch. You have to give up some precision on your range to be that confident. So in other words, I could give you a 95% confidence interval and say, oh, well, the temperature is going to be somewhere between 95 and 105 degrees, and I'm 95% sure that temperature is going to fall between these two numbers, 95 and 105. And then you say, that's not good enough. I want you to be 99% confident in what the temp's going to be, or the bracket for the temp. And so I say to you, all right, you want 99% confidence? Well, it's going to be somewhere between 0 degrees and 120 degrees, and I'm 99% sure of that. So when you want to have more confidence in your estimation of the population mean, that it's between your two values, you give up some precision in that range. You end up with a wider range of numbers. But you could be more precise if you are 95% confident. You can give a smaller range that helps people, get a more precise understanding of where that population would mean, but you do give up some confidence. Okay, so to dive a little deeper into this concept of confidence intervals, we're now going to talk about doing confidence intervals when we have a actual population parameter, which again is theoretical in nature because we never would actually have a population parameter, or in most cases we wouldn't. So using the normal curve to calculate confidence intervals when the population standard deviation is known. That's that sigma symbol there. So a probability value can be calculated that indicates the degree of confidence we might have that our population mean really is in this interval. So typically we like to be at least 95% sure that the predicted population mean falls within our confidence interval. And so that's what I was referencing on the previous slide when I said there's two types of confidence intervals, the 95% confidence interval or the 99% confidence interval. Here they're written as decimals, so the 0.95 confidence interval, what we would use to calculate it is plus or minus a z-score of 1.96 multiplied by the standard deviation of the entire distribution of sampling means plus the mean. So you may be wondering, why are we going to be using a z-score of plus or minus 1.96 in this 95% confidence interval formula? And the answer is because if you look down at the normal curve on the bottom right of your screen, you see where 95% of the scores fall, and those are marked off by the negative 1.96 z-score. And the upper limit of that 95% bracket is the positive 1.96 z-score. So we know that 95% of cases fall between those two z-scores. And so we're able to be 95% confident that our population mean is going to be within those two z-scores. Any value that would fall beyond a z-score, positive or negative, of 1.96 leads to the conclusion that the mean is not part of the known population. So in other words, if you were, plotting your two values that you get from doing your confidence interval formula, and, side note, we're not going to be using these formulas to calculate confidence intervals because these formulas rely on having certain parameters, and we don't have parameters because we haven't measured, or we can't measure the population. So, if you were, though, to use, your confidence interval formula and get your two values and then plot them on the normal curve, at the 95% confidence interval, if that was, the formula you had just used, your two values would fall at the 1.96 z-score and the negative 1.96 z-score. And then if you were to do the 99% confidence interval formula, which I'll be showing you on an upcoming slide, when you do that formula, the two raw scores that you get should fall right at the 2.58 z-score and the negative 2.58 z-score. So any value that falls beyond that leads to the conclusion that the mean is not part of the known population. And beyond that just means, more than. So more than 2.58 positive or negative. So like if it's out on the tails of those curves, then we would say it's not part of the known population. But we can say that we're 99% confident that the value we come up with from doing this calculation is, somewhere between the 99% area of the curve that's marked off. But since we usually don't know the population standard deviation, we can't calculate confidence intervals this way. So I am going to be showing you the confidence interval formula that we're going to be using. And the confidence interval formulas that we're going to be using are based off scores from a sample. So we're using the scores from the sample to give a bracket that estimates where the population mean would fall. So in order to calculate confidence intervals, we have to use what's called the t-distribution. So far you know about the normal distribution, which I like to think of as the x distribution because it's like x for raw score, but no one calls it that except for me. Anyways, and then you know the z-score distribution, and now you have what's known as the t-distribution. Lowercase t, not to be confused with the uppercase t scores we discussed earlier in the semester. So what you can think of when you think of the t-distribution is a normal curve with these lowercase t values on the bottom, on the x-axis or the abscissa. And what the t-distribution is becoming is a new basis of comparison for the sample that we're working with and trying to calculate confidence intervals for. And so we can use the t-distribution. We have to use the t-distribution to calculate confidence intervals, but we can also use it when the sample standard deviation is unknown, or if you have a small sample size, like an N of 30 people or less. And usually our population standard deviation is unknown, and with sampling, because we're normally, taking, like the example we used, 30 people at a time, and giving them an IQ test or whatever it is that we're measuring. With sampling, we often have that small n because we're doing these small groups of people at a time. But the smaller the sample size, the less certain we are of normality of the entire sampling distribution. Therefore, we use a t-distribution, which is a family of distributions, each of which deviates from normality depending on sample size. So it's basically a distribution like the normal curve that we're going to use as a basis of comparison, but it's created of all of these t values on the abscissa, and the t values are comprised based on sample size. So those values in the t-distribution are distinguished or created, separated by their degrees of freedom, and that's what's based on sample size. So the way we calculate what's called degrees of freedom is by taking n minus 1. So Another thing that you need to know for the quiz is that as the degrees of freedom increases, and what causes degrees of freedom to increase is the number of people in your sample or the number of people in your sampling distribution. So as the degrees of freedom increases, the t-distribution becomes more like the normal distribution. So the more people that you have, the more likely the shape of your data is going to be mesokurtic or a normal curve. So there is a term that you need to know because you're going to be using it a lot going forward, and that term is critical values. So the critical values are on the t-distribution at the 0.05 and the 0.01 levels, where 0.05 represents the 95% confidence interval levels and the 0.01 represents the 99% confidence levels. So if you picture the curve, the critical values are going to be in the tails of the curve. And so we are going to find where we mark off those critical values by referencing table C, which is the t-distribution. And so we're going to look up on these columns, the 95% column and the 99, or the 0.05 and the 0.01. We're going to look in these columns for what are called critical values. And that's where we're going to mark off the 95% of the distribution and the 99 middlemost percent of the distribution. And so any value that we get that falls outside of that middle 99 or 95% area of the curve is going to not be part of our population. And so that's what we are going to be using this t-distribution for. So all the values on table C create a bunch of different t-distributions with these critical values marked off. And so table C is giving you the marked off critical values depending on how many people are in your sample, since we use the number of people in our sample to get our degrees of freedom calculation, and the degrees of freedom are what you need to get the critical values from table C. And so, fun fact, this guy on your screen is William Seeley Gossett, and he is the developer of this t-distribution. So we're going to use old Bill's t-distribution. Bill, okay. We're going to use the t-distribution to determine our critical values. And so the reason we need critical values is to calculate these confidence intervals that will allow us to estimate the population mean with either 95 or 99% confidence. So something to note is that critical values of t should be calculated using 3 digits after the decimal, because that is how they appear in table C and D. So normally, it's the critical values for T are also on table D, but we'll talk about that later. Let's just focus on table C for right now. So they are going to be presented on table C in with 3 digits after the decimal. And so when we put the critical values into our confidence interval formula, we have to honor the 3-digit after the decimal format. So we put the numbers into our formula as they appear on the table, but then after the first calculation with that table C value, we begin rounding as normal. So we round to 2 digits after the decimal. So we just plug it in to the formula as we see it on the table, but then as we calculate through as normal, rounding at each step of the calculation. So to calculate confidence intervals, I'm going to show you this on the tutorial coming up. So you're going to need that standard error of the mean worksheet, because we're going to do the confidence intervals portion of it, which is the bottom half. And so to do that, you're going to have to first calculate your degrees of freedom for your sample, and that's easy. It's just the number of people in your sample minus 1. Then you're going to go to table C, and using those degrees of freedom, you're going to get the 0.05 value and the 0.01 value, depending on if you're calculating the 95 or the 99% confidence interval. And then you are going to plug those values into this formula that you see here below. And so when you calculate the 95% confidence interval, you have to put the values that you got at the 0.05 level on table C into the formula, and you have to do the formula twice. So the first time you put the critical value of the t at 0.05 into your 95% confidence interval, you're going to put it as a positive, and the second time you're going to put it in as a negative. You're also going to enter in the standard error of the mean and the mean. So you're going to multiply the value you get from table C at the 0.05 by the standard error of the mean plus the mean. Then you're going to do it again with the table value that you get from table C at the 0.05 level as a negative number multiplied by the standard error of the mean plus the mean. And when you do the formula with the positive value from table C, you're going to get the upper limit of the confidence interval, the higher number. And when you do it with the t value that you get from table C as a negative number, the number that you get when you calculate through the formula is going to be the lower limit of your confidence interval, or the lower number. And the same is going to be true of how you calculate the 99% confidence interval. The only difference is that instead of getting the numbers from table C on the 0.05 column, you're going to grab them from the 0.01 column. And so your answer for the 95% confidence interval is going to consist of two numbers, and the answer for the 99% confidence interval is also going to consist of two numbers. So I'll show you what I mean on the worksheet here. And now we're going to go ahead and calculate confidence intervals. So to calculate confidence intervals, we need to complete this formula here. And since a confidence interval represents a range with a lower limit and an upper limit, we have to do this formula twice so that we can get the confidence intervals at both anchors of this range. So I'm going to just start by writing out my formula here. I'm going to do it twice. So it says t.05, and that's going to be plus or minus, so let me do that twice. And then the standard error of the mean plus the mean. Okay, so this is the formula for a 95% confidence interval. It uses the critical values from the 0.05 column on table C. And in order to get the critical values at the 0.05 level on table C, you're going to need degrees of freedom. So degrees of freedom is your n, which is in this case 15. So 15 minus 1 equals 14. So our degrees of freedom are 14. So using that information, I'm going to go to table C, and I'm going to look at 14 degrees of freedom here. And on 14 degrees of freedom, there's two values. One is at the 0.05 column and one is in the 0.01 column. So I'm actually going to be calculating the 95% confidence interval here. So I'm going to use the level of significance at the 0.05 because 100 minus 0.05 is 0.95. And so we're trying to get the 95% confidence interval, so we're going to use the 0.05 column. So we have 2.145, and so 2.145 is going to be our t-crit value that we plug in here, so 2.145. And to get the upper limit and lower limit of our confidence interval, we need to do this formula twice. Once with this t-value as a positive number, and then once with it as a negative number. And that's how we're going to get our lower limit. So I'm going to make this crit value positive once, and then in the next time I do the formula, negative. So positive and negative crit values. Then the rest is going to be the same. I'm just going to plug in the standard error of the mean, which we just calculated as 0.67. So I'll plug it into both. The mean for the above problem is 10.19. So I'll put that there. Okay, so if I were to calculate through this, the first thing that I would need to do is this multiplication here. So if I did that multiplication, 2.145 times 0.67, I would get 1.437. And then down here, if I do this multiplication of negative 2.145 times 0.67, then I would just get negative 1.437. Okay, so now I'm just going to finish out the formula. I have not included the mean yet, so I'm going to add that. And when I calculate through that, I get 11.63 as my upper limit, and I get 8.75 as my lower limit. So when I report my answer for this 95% confidence interval, I would just say that the 95% confidence interval is 8.75 to 11.63. And you are going to do that dash in between. It's a little bit longer than a subtraction symbol. And the lower number always has to go first when reporting your numbers here. So you always do the lower limit and then the upper limit. And so if you were asked on the quiz, what does this confidence interval tell you? What you would say is that you are 95% sure that the population mean or the population mu would fall somewhere between these two values. So I'm 95% confident, or I'm 95% sure that the population mean, the estimated population mean, is going to fall somewhere between 8.75 and 11.63. So make sure that you have what I just said written in your notes, because it is an upcoming quiz question. What does a 95% confidence interval tell you? Tells you that you're 95% confident the estimated population mean is somewhere between these two values, 8.75 and 11.63. Okay, let's do the 99% confidence interval now. And so it's the same process, but instead of looking in the 0.05, instead of looking in the 0.05 column, we're going to look in the 0.01 column. So I'm going to start by writing out my confidence interval formula again. So I'm going to have my t.01 times my standard error of the mean plus the mean, and then t.01, this time negative, standard error of the mean plus the mean. Okay, so degrees of freedom are still 14. 15 is the end, so 15 minus 1 gives us 14. So using 14 degrees of freedom, we're going to go to table C. And we're going to look at the 0.01 column where it says 2.977. And that's going to be the value that we're going to plug in here. $2.977. Okay, so now that I have positive 2.977 and negative 2.977 plugged in, I'm just going to go ahead and get my standard error of the mean. It's going to be the same for both of these 99% confidence interval calculations. Same with the mean. You can use the mean of 10.19 for both. And then I'm going to go ahead and calculate through. If I do 2.977 times 0.67, I would get 1.99. And I would get negative 1.99 if I multiplied negative 2.977 times 0.67. Okay, so I'm going to add the mean to those values now and calculate through. And when I calculate through, that's going to give me an upper limit of 12.18 and a lower limit of 8.20. So if I were to report this confidence interval, I would need to start with the smaller value first, followed by a long dash, and then the larger value, also known as the upper limit. Okay, and that is a 99% confidence interval. So if I was to ask you on the quiz, what do these numbers tell you? What you would say is that you're 99% sure that the estimated population mean falls somewhere between 8.20 and 12.18. And then just before I end this tutorial, I just wanted to make a suggestion to you that you start noting what the tables are for. We're going to use table C for a couple different tests. And then also you're just going to be getting a lot more tables, and so they can get kind of confusing. But just take a second to familiarize yourself with this table here. It says critical values of T, and then it gives you, your columns. They wrap around. Notice this infinity symbol here. On an upcoming quiz, you're going to be asked to use the infinity symbol rather than a calculated degrees of freedom. And you'll just look here and use 1.960 in the 0.05 column, and you'll use 2.576 in the 0.01 column. So look for this one on the quiz. Make sure you use that infinity symbol. But I would go ahead and start labeling up these tables, like I said. So table C are your critical values of T. And we use our critical values of T for our confidence intervals. So I would write confidence intervals on here, and then I would also write the degrees of freedom calculation because they vary from test to test or statistic to statistic. So you'll need to know what each is, and it's easier to just have it all here right next to the table that you're referencing. So another thing that we can do with the t-distribution, thanks to William Seeley Gossett, is we can do hypothesis testing using a statistical analysis called one-sample t-test. So we can use t-test to answer research questions or test a hypothesis. And t-test answers statistical questions such as, one, is the difference between the sample mean and the population mean statistically significant? So let me illustrate this for you. I, like a lot of moms, think that my daughters are geniuses, well above the average IQ. Are they really? I don't know. They're like 2 and 5. I haven't had them tested, and I don't want to know the answer anyways because I'm biased and I like to just think that they're geniuses. But if I did want to know, I could get their IQ and find out the average IQ and then run a one-sample t-test and see, are they right there at the norm 100 IQ, right there at the average, or are they far away from the average? Is their IQ significantly higher or lower than the average? And so then the next question is, well, what constitutes significantly higher or lower than the average IQ? And so we would say, if we wanted to tell you with 95% confidence that my daughter is significantly different from the mean, then we would say that they need to be above or below 1.96 standard deviations, right? And if we wanted to say with 99% confidence that my daughter was statistically significantly smarter than the average, then we would need to have her score fall at the z-score of 2.58 higher or lower, because that's the z-score that represents the 99% of most cases, or the 99% confidence level. So if I were to tell you that my daughter was tested and the average IQ was 100 and my daughter's IQ was 101, so I've done it, I've shown that she's smarter than everyone else, hypothesis confirmed. You might say to me, lady, you're crazy. A 1-point difference between the average IQ and your daughter's IQ does not make her a genius, right? That is not a statistically significant difference. So to find out if the difference is significant statistically, we have to see if it falls outside of that 1.96 z-score or that 2.58 z-score. Or in this case, since it's a one-sample t-test, we need to see if it falls outside of the critical values that we are marking off using the t-distribution at the 0.05, aka 95% confidence level, or the 0.01, aka 99% confidence level. So in order for my daughter to be significantly smarter than everyone else, she would have to fall outside of that 95% or 99% where everyone else falls in the curve, right? And then for number 2, we could answer the statistical question, what is the probability that a sample mean could deviate from the population mean the amount that it does? And so that's where we use our 95% and our 99%. And then finally, is this sample from the population or not? Is my daughter from the population of average smarties, or is she outside of that, either being super, super genius or super, super dumb? That sounds terrible. So at any rate, these are the questions that a one-sample t-test can address. And so here's another example research problem. A researcher theorizes that the population mean among college students taking the new social conformity test is a neutral 100. Scores higher than 100 represent more conformity than average, and scores lower than 100 represent less conformity than average. A random sample of 30 students was selected and found to have a mean of 103 with a standard deviation of 10.83. Using the t-test, what statistical questions could we ask about this problem? Well, we could ask, is the difference between the sample mean, which here was 103, and the population mean, which here was 100, statistically significantly different? So our one sample t-test could answer that question for us. And then what is the probability that this sample mean of 103 could deviate from the population mean of 100, the amount that it does. And so we'll be able to say that with 95% probability or 99% probability. And then the last one is this sample, is this sample of these students with the mean of 103, is that sample mean representative of the population? Is this sample from the population or not? If that 103 was a significantly higher or lower mean, we would say no, but our one sample t-test is probably not going to find that mean of 103 is significantly different from a mean of 100. And if that's the case, then we would say that the sample is from the population. Okay, so let's talk more about these hypotheses. So a one sample t-test allows us to test a hypothesis, but there's a weird thing about the way we test hypothesis in the social sciences, and that is that we don't test our actual hypothesis. We test what's called the null hypothesis, or the hypothesis of no difference, the hypothesis of nothing to see here. So why would we do that? Why wouldn't we just test our actual hypothesis? And the answer is because we want to do our hypothesis testing as unbiased and as objective as possible. So rather than me going into my study saying my daughter's going to be smarter than everyone else, which could, if that's my attitude, it could consciously or unconsciously bias the way I select my sample, or bias the way I interpret the data, or even calculate through the data. And so I want to go into my study as unbiased as possible, and that's something that the HO, or the null hypothesis, allows us to do. So you see the HO there is symbolized with mu1 equals mu2, meaning my daughter is going to be equal to the rest of the population. She's not going to be any smarter or any dumber. She's going to be the same. And so we would say there is no significant difference between the sample mean and the population mean if we wanted to verbalize what those symbols mean. So on your quizzes coming up, you are going to be asked to put null hypotheses for certain tests. In this case, we're looking at the one sample t-test, but you're going to be asked to put hypotheses in symbolic form. And so if you're asked to put the null hypotheses in symbolic form for the one sample t, you would put mu1 equals mu2, which means there's no difference between the sample and the population, or the sample is from the population. They are one and the same. Now our actual hypothesis is called the alternate hypothesis, and it's symbolized by HA, or some people symbolize it with H1 as the subscript. And here you can see that symbolically it's saying the mu for group 1 is not going to be equal to the mu for group 2. And so just as a side note, the mu1 is our sample mean, or our point estimate. And it's written there as a mu symbolically because theoretically it's an estimate of our population mean. And so it's represented as a population parameter symbol, a Greek symbol. So the alternate hypothesis is the hypothesis of difference that says the sample means deviates enough from that population mean. My daughter is, her IQ score is far enough away from that average IQ score of 100 that I can conclude that the sample, my daughter, is not from the population of people with an average intelligence. Okay, so how do we calculate a one sample t-test? Well, I'm going to be showing you on the one sample t-test worksheet, so you'll need to grab that off of Canvas, and I'll be showing you that tutorial momentarily. But I'm just going to talk you through it first, and then we'll do the example together. So the first thing that you need to do is determine the number of degrees of freedom you have, and that is calculated by just taking n minus 1, and then you are going to calculate a t-value for your sample mean so that you can see its relation to the population mean. And so to calculate a t-value, you're going to take the sample mean, which you may have to calculate if it's not explicitly given in the word problem. You might just have a set of values, individual scores that you have to calculate the mean from. And then you're going to subtract the mu, which is the population mean, and that will be given in the word problem. There's no calculation you could do to get that. It's just going to be a value that is written there. And then you are going to divide that by the standard error of the mean, which you know how to calculate. And so if we were to do this one sample t-test using the previous example, you could see it worked out there. We take the standard error of the mean, we divide the standard deviation into the square root of n minus 1, and that would give us 2.01. And then we would be able to take that SEM of 2.01 and plug it into our t formula. So we would put the mean of 103 minus the mu of the given mu of 100, and then that would be divided by that standard error of the mean that we just calculated, 2.01, and that would give us a t-value of 1.49. So now that we have this t-value, we're like, cool, what does this mean? We don't know yet. We have to go to table C and get our critical values that mark off outside of the 95% of the curve and see if our t-value is outside of that 95%, so significantly different from the 95% middlemost of the curve, or, if it's in there, if it's in the same population as everyone else, if it's inside that 95% of people. And so you need to look at table C to get what we call your critical values, or your t-crits, as we call them on the statistics streets. So to get your t-crit, you got to go to table C, use your degrees of freedom, and then if you're looking for the 0.05 level t-crit, so you can be 95% confident in your findings, you're going to look at the 0.05 column. But if you want to be 99% confident, you look at the 0.01 column, and you use your degrees of freedom, and then you make a little intersect with your fingers, and that's the crit value that you're going to report, and compare your calculated t-value, the one that you just did that formula for, your calculated t-value, you're going to compare that against the values you get on table C. So if your calculated t-value is equal to or greater than the table value, then you reject the null hypothesis, as we say. We cannot reject our null hypothesis in this example here in the highlighted yellow, where we got the t of 1.49. We would not be able to reject because the table value at the 0.05 level on table C with 29 degrees of freedom is 2.045. So we would have to conclude that there is no significant difference between the sample mean and the population mean. And when we do that, we accept HO. So when we finish calculating through and getting our t-value, we compare it to the normal curve and see if it falls within the middle kind of area of the curve where everyone else, 95% of people are, or 99% of people are. And if it falls outside of that range, then we get to reject HO. And we also report the level that we reject. If it was rejected at the 0.05 level, meaning it fell in the tails of the curve that we had chunked off as the 0.05 level, which I'll be showing you coming up, or if it's if our sample t, our t-value that we calculated, if it falls in the 0.01 chunk of the tail. So again, I'll show you that coming up, but you have to reject HO if it falls in those areas of the tail at the appropriate level of significance, and if it does not fall in the tails but instead is within that 95% area of the curve, then you have to accept HO. So in order to reject HO then, the t-values must fall within the 0.05 or 0.01 critical areas. And using the previous example, let's say we did reject the null hypothesis, which in turn means that we accepted the alternate hypothesis. Then we must now say how unlikely our null hypothesis is. So instead of saying it is highly unlikely that there is not a difference between the sample mean and the population mean, or instead of saying it is highly unlikely that our sample mean is from our population, we would say there is a significant difference between the population mean and the sample mean. Or we could say the means of the sample mean and the population mean have found to be significantly different. In other words, the probability that the groups are the same or that the sample mean is from the population is very, very low. And so you might be asking, well, how low is very, very low? And that would be when the probability that the groups or means are the same is less than 5% or 1%. In other words, there is less than a 5% chance that these groups, the sample and the population, are the same. And so significance levels are called alpha levels or critical values and are represented by alpha symbol. So there's the little A, kind of curly A, or they're represented by p-values. And so this is how we normally represent them. So when we reject HO, we are saying we reject HO at either the 0.05 or the 0.01 level. And so on your homework and stuff, there's going to be a spot for you to check mark accept HO or check mark reject HO. And if you check mark reject HO, there then is going to be a spot for you to report the level at which you reject. So either P less than 0.05 or P less than 0.01. And again, if you report P less than 0.01, that means that the T value you calculated fell in that area of the tails of the curve. And verbally, you would say that there is less than a 5% or less than a 1% chance that these groups, the sample and the population, are the same, that there's not a significant difference between them.
That is very much adequate.
So I'm going to show you all of this on the One Sample T worksheet. So go ahead and grab that and then we'll go through it together. And I think this will become a lot clearer. Okay, welcome to the One Sample T-Test worksheet. Number 1 reads, on a nationally standardized reading comprehension test, the norm for the population mean was designed to yield a score value of 50 for the population of 5th grade students. A random sample of 10 elementary school children was tested, yielding the scores that follow. So these scores over here. Determine whether this sample might be representative of the population for whom the test was designed. So a couple values popped out at me and I'm just going to write them off to the side so I have them when I'm ready to complete my formula here. But one that popped out was the mu, so the score value of 50 for the population. So the population mean is going to be 50, so I'm going to put that here and where the mu symbol is. And then also I saw that this was a sample of 10 elementary school kids. So N is going to be 10. So I'm going to put that right here. Okay, so those were the values that popped out at me. And to solve for this, since I have one sample that I'm comparing to the population and I have interval data, I'm going to do a one sample T. And so for one sample T, I need my mean, my mu, and my standard error of the mean. So let's go ahead and write down the values that we already have. So we already have the mu of 50, and we don't have the mean or the standard error of the mean. But I can calculate the mean very easily by coming to these raw scores over here and adding them all up. So if I add up all these raw scores, I would get 448. And then I would divide them by 10 because 10 is my N. And that would give me 44.8. Okay, so now that I have my mean, I can go ahead and plug it in to my formula. So my sample mean is 44.80 minus my population mean of 50. And then the next value that I'm going to need is this one here, the standard error of the mean. So my standard error of the mean calculation is here. The standard error of the mean calculation requires the mean that we have already, the N, which we already have, and it also requires sigma x squared. So we're going to have to square all our raw scores and add them up. Let me go ahead and write my mean on here. Okay. So if we were to square all of these scores and add them up, I'm not going to do it this time. You'll just have to take my word for it. If we squared each of them and then added them all together, we would get 20,362. Okay, so now we have all of our puzzle pieces to calculate through this SEM formula. So I'm going to start plugging them in here. So my sigma x squared is 20,362 over my n of 10. Also 10 is going to go down here. 10 minus 1 on the denominator. And then that numerator is going to be subtracted from the mean squared. So 44.8 squared. Okay, so if I calculate through this standard error of the mean formula, I'm going to start by doing this division on the numerator. And that is going to give me 2,036.2. And then the mean squared is 2007.04. And we would divide that by 9 because 10 minus 1 is 9. And then when we do the subtraction there, that would give us 29.16. So the subtraction on the numerator gives us 29.16 divided by 9. Do that division, you're going to get 3.24. And when you take the square root of 3.24, you're going to get 1.80. So your standard error of the mean is 1.80. That was your missing puzzle piece to your t-test, so you're able to plug that in now. So if I calculate through this t-test, on the numerator, I'm going to get negative 5.2 over, I'm just carrying down that denominator, 1.8. And if I do that division there, that's going to give me a t of negative 2.89. And that is my final answer. So I'm going to put negative 2.89 on my answer line. And so because this is a two-tailed test, meaning that it just wants to know if there is a difference between the sample and the population, or if the sample is the same or representative of the population, but it's not making a prediction about the sample being higher or lower than the population. It just wants to know if there is a difference between the two. So when it's asking if there is a difference between the two, the sample and the population, we are able to put our critical values on either side of the curve, on both tails of the curve. And because of that, it is called a two-tailed test. So we're going to get those critical values from Table C. Table C is the table we use if we have a two-tailed test, whereas Table D is the table we use if we have a one-tailed test. But here on problem 1, since we have a two-tailed test, we're going to use Table C to get our degrees of freedom for a one-sample t-test. And so for a one-sample t-test, the degrees of freedom calculation is the same as confidence intervals, n minus 1. So I'm going to do n minus 1 here to get my degrees of freedom. 10 minus 1 equals 9. So I'm going to put 9 in these parentheses to let my reader know that I am using 9 degrees of freedom to get my crit value at the 0.05 level and the 0.01 level. So I'm going to go ahead and get those values. And because it's two-tail, I'm going to write them as positive or negative. So for the 9 degrees of freedom at the 0.05 is 2.262 plus or minus 2.262. And at the 0.01, it's going to be plus or minus 3.250. Okay, so now that I have my crit values, I'm going to plot them on my curve. So I'm going to draw my curve. And I'm going to say that The 0.05 is about here on both sides, and the 0.01 is about here on both sides. I like to do a little shading just for some delineation, you know. So I mark off the 0.05 chunk as a dash, and I marked off the 0.01 as dots. So the 0.05 crit value is 2.262. So I'm going to write this 2 times, once on the positive side of the curve as a positive, and once on the negative side as a negative. And then I'm going to write the 0.01 crit value, which is 3.250, and negative 3.250. Okay, so then I am going to take my t-value. Here would be my mean of 0, right? I'm going to take my t-value and see where it would fall on my curve. If it falls in these shaded chunks here, I get to reject HO. Same thing on this side. If it falls in those areas there, I get to reject HO at the appropriate level. So either if my t-value falls in the 0.05 chunk, then I would say reject HO p less than 0.05. If it falls in the 0.01 chunk, then I would say reject HO p less than 0.01. And if it falls in the middle of the curve, then I would say accept HO. Okay, so let's test the hypothesis that the sample is significantly different from the population by placing our calculated t-value on our curve so we can compare it. So negative 2.89, I would say is going to fall about right here. T equals negative 2.89. So that's going to fall in my 0.05 chunk. So my decision here is going to be reject p less than 0.05. So if it had fallen in the dotted area at the 0.01, I would write the same thing except change the 5 to a 1. And if my t-value had fallen in the middle, I would check accept HO. Okay, so we're going to pause there because the second problem on the worksheet is just a little different. So we're going to work up to that, but I got to tell you a few more conceptual things first. So type 1 error is what we're going to talk about now, and that's pretty heavy on the exams, well, the final exam and the quiz. So you want to make sure you understand this very important statistics concept. So we use strict levels of significance to reduce the probability of committing what we call a type 1 error, which is also known as an alpha error. There is another type of error called type 2 error or beta error, but we're not going to talk about that today. I'll save that for another day. So alpha error is when we reject the null hypothesis, symbolized as HO, but we should have actually accepted it. So we said there was a difference between the groups when there wasn't. I said there was a difference, a statistically significant difference between my daughter's IQ and the rest of the groups when there wasn't one. Could you imagine how embarrassing, right? So researchers really want to avoid a type 1 error. It does happen in real life in the field, and it's like super embarrassing. It's not great for your reputation. It kind of makes you look reactive and like overzealous, or that you're not understanding how to interpret your statistics correctly, or that you didn't do your study correctly. You lacked validity or reliability. So it's not the best look, and it's potentially dangerous to society to say, like, you know, we found that this cancer drug works significantly better in reducing cancer cells than this drug. If you're wrong in that, then, you know, you could be putting like people's lives at risk. So due to the basic conservatism of scientists, we would really prefer to not commit this type 1 error in saying that, you know, we found something significant when we didn't. So the probability then that we kind of set as researchers that we're comfortable with, the probability of making a type 1 error is equal to what we call alpha, 0.05 or 0.01, those critical levels, those significance levels. So p less than 0.05, or it could be symbolized as alpha less than 0.05, means that the probability of making a mistake and rejecting HO is less than 5 in 100. In other words, at the 0.95 significance level, we are willing to make a mistake in rejecting HO 5% of the time. And when we are using a probability of 0.01, this means that the probability of making a mistake and rejecting HO is less than 1 in 100. And so at the 0.99 significance level, we are willing to make a mistake in rejecting HO 1% of the time. Okay, so when I was doing the example with my daughter, saying that she was going to be smarter than the normal, her IQ was going to be significantly different than the norm IQ of 100. If I wanted to test that theory or test that hypothesis, I would test the null hypothesis, of course. And there's really two types of null hypotheses that you can test using a one sample t. You can test what's called a two-tail hypothesis or a one-tail hypothesis. So a two-tail hypothesis tests questions like, is there a difference between your sample and your population? Or is there a difference, between the sample group and the population group? And so when you want to know just if there's a difference, you as the researcher have not made a prediction about whether your sample is going to be higher or lower than the mean. You have just made a prediction that it's going to be different than the mean, right? So if I was to say, I don't think my daughter is right at the mean IQ of 100. I think she's different from that. Then I would do a two-tail one sample test. And so to identify a two-tail test on your word problems, you just need to look for difference, representative, different, those types of words. They're non-directional words. They don't specify the direction of the difference. If your sample is going to be on the right side, the right direction, the right side of the population mean, or the left side of the population mean. It just wants to know if there's a difference. So when that's the case, it doesn't matter if your calculated t-value is positive or negative. As long as your calculated t-value is a bigger number than the critical value that you get on table C, you're able to reject HO. So the critical values on table C are going to be given as a positive. But if you do calculate a one sample t and you get a negative number, you could just go ahead and put a negative number in front of the values that you get from table C. That's not the case with all statistical tests, but with a two-tail, it's safe to do that. So if you calculate a negative one sample t value, then you're just going to take the values you get off of table C and throw a negative in front of them. However, you cannot do that with a one-tail test. So a one-tail test, or what we call a directional test, the hypothesis contains a prediction about where the sample t is going to fall on the curve. It predicts if the sample t is going to fall on the right side of the curve, or the hypothesis will predict if the calculated t-value is going to fall on the left side of the curve. So then your hypothesis becomes very important in determining if you should make your critical values negative or positive. So we use table D for critical values when we have a one-tail test. And I know I have a one-tail test if in the research design or the word problem on my homework and quiz has these directional words. If the researcher makes a prediction about how its sample is going to perform in comparison to the population mean, or the population. So if the researcher predicts that one group is going to perform better or worse, score higher or lower, if a researcher predicts that one drug is going to be more or less likely to be effective, if I predict that my daughter is going to be brighter or dumber, these are all directional words in my hypothesis. And when I have directional words, I know I need to use this one-tail test, meaning that I get to put my critical values on the one tail of the curve that coincides with my hypothesis. So if I'm predicting one group to perform better, I'm predicting a positive t. If I'm predicting my sample to perform worse, I'm predicting a negative t. If I'm predicting my sample to score higher, I'm predicting a positive t. If I'm predicting my sample to score lower than the population, I'm predicting a negative t, and so on and so forth. So whichever t I predict, whether it be negative or positive, I have to make my critical values that same sign. So if my t-value is predicted to be positive, then I have to make my crit values positive. If I predict my t-value to be negative, then I have to make the values that I get off of table C negative. And so if you hypothesis a positive t-value but you get a negative one, game over. You have to accept HO, even if it's larger than the table value without the appropriate sign. Okay, so look for those directional words in the hypotheses. If you see a directional word, you know it's a one-tail. If you don't see any directional words and instead you see words like difference, differently, different, representative, not representative, then those are going to be indications of a two-tail test. So here is an example of a one-tail, one sample t-test on your worksheet. Okay, so let's look at number 2. The superintendent of Zodi School District claims that the children in her district are brighter on average than the general population of students. In order to determine the aptitude of school children in the district, a study was conducted. The results were as follows. Test the hypothesis that the Zodi children are brighter than the general population, assuming that T equals 2.024 and there's an N of 30. So this particular test is going to be a one-tail test. And the reason that it's one-tail is because of this word brighter. So brighter is a directional word, and these researchers are guessing that the Zodi children, the sample, is going to do better than the population, that they're going to be brighter than the general population. So when we have our curve here, right, our normal curve, we know that positive numbers go on the right of the mean and negative numbers go on the left of the mean. And we also know that the mean is in the middle. So if this is the population mu here in the middle, and we want to know where our sample falls compared to this normal curve for the population, right? Population means here in the middle. And we're predicting that our children are brighter. That means that we're predicting that our sample, our Zodi sample, is going to be on the right side of the curve, that they're going to be brighter than this mean, that they're going to be above this mean. Their values are going to reflect higher scores than this mean. If, which we're not, but if we were predicting that the Zodi children were going to be dumber, then we would be predicting a negative t-score, okay? But because we're predicting that the students are going to be brighter than the population, this is the population, our sample is the t-value here. We're predicting that our t-value is going to be above the population. So we're predicting a positive t-value. And so when you predict a positive t-value, then you have to make your critical values positive. And so you cannot do what you can do in a two-tail test where you can put critical values on both sides of the curve. If you make a prediction using directional words like brighter, higher, more, above, bigger, greater, or negative directional words like below, worse, less than, if you use those words, then you're only allowed to put critical values on one side of the curve, the side of the curve that you're predicting your sample is going to fall on. So we're predicting that our sample is going to be smarter than the population, that they're going to be on the positive side. So we have to get a positive t-value in order to be able to reject HO. So if we predict a positive t-value but get a negative t-value, then we automatically accept HO. But if we predict a positive t-value like we did with this hypothesis, and we get a positive t-value like we did here, then our critical values have to be positive, and we have to also make sure that we fall in the rejection region in order to support the hypothesis, just like above. So I'll show you what I mean. Let's get these critical values and plot them on the one tail of the curve where the researchers predicted their sample would fall. So N of 30 is going to give us degrees of freedom of 29, because 30 minus 1 is 29. And we're actually going to use table D because table D is for a one-tail test. So I'm going to put one sample T down here. And it's the same degrees of freedom n minus 1. And you might just want to write yourself a little note that this is for two-tail. Table C is for two-tail. And table D is for one-tail. Although it does say it here as well. Okay, so because there's this directional word brighter, this is a one-tailed test. Our degrees of freedom are 29. We're going to come down here to our table for our one-tailed test, which is table D. We're going to look at 29 degrees of freedom. And the 0.05 is 1.699. So I'm going to plot that here on the positive side since I predicted a positive t-value. And the 0.05 or the 0.01 is 2.462. Okay. So 0.05 and 0.01. So I'm going to go ahead and mark off 0.05 and then dots for the 0.01. Okay, so let's see where our t-value would fall in comparison to this normal curve for the population. Remember the mu for the population is in the middle. If we get our calculated t-value, if it falls anywhere outside of this shaded area, the 0.05 chunk or the 0.01 chunk, anywhere outside of it, we have to reject HO. So, we have to accept HO. So what we're going to do is, let's write these down real quick, 1.699 and 2.462. And then I'm going to take my t-value that was calculated for us and see where it falls. So I would say, starting at 0, going beep, 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 2.024 would be about here. In my 0.05 region. So I am going to, again, reject HO, P less than 0.05 because my calculated t-value falls in that 0.05 chunk. If this value had been calculated and found to be negative, we would have to accept HO because we predicted a positive. So if we predict a positive, we have to get a positive t-value. And that is a one sample t-test, one tail and two tail. Okay, so that concludes chapter 8. Thanks for listening. I'll talk to you on the next one. Have a good day.